Hello again, Kristian Krabbenhoft from the University of Liverpool. In this video I am going to say a few words about what we call random field analysis in OptumCE. We have some material on it both in the theory manual but also in the examples manual, and I will just open up the examples manual and search for random field or stochastic analysis. That's another way of putting it. So we all know that soils are notoriously variable. The properties are notoriously variable. They vary with depth, and they can also vary quite rapidly with spatial location. So the properties taken from one borehole may be quite different from those taken from another borehole at some distance away from the first one. And the question is how to account for this variability in a, let's say, in a meaningful or consistent or rigorous manner. And one way of doing it is with the use of random field analysis. So the idea with random field analysis is that instead of considering just one fixed value of a given parameter, we consider a probability distribution of that parameter. So we suppose that we go out into the field and then we do 1,000 tests for the, say, the undrained shear strength, and then we might find that it is distributed in this type of fashion here. This is a so-called log normal distribution. We have the undrained shear strength here and the frequency here. If you want to look at the cumulative probability distribution function, it looks something like this. So the mean value here is, I don't know what it is exactly, about 70 kPa, and then there is some standard deviation as well. Roughly speaking, the width of this curve here. So there are two parameters, the mean value and the standard deviation. But that's not all, because there's also some spatial variability. Say if you were to do an analysis of a footing, instead of having a deterministic parameter, you would say, instead of having a deterministic undrained shear strength, you would say, okay, the shear strength follows a probability distribution like this. Then you would do 1,000 tests where you pick a value from this distribution at random. So you could pick a number between 0 and 1, generate a random number between 0 and 1, and then read off the corresponding undrained shear strength from the plot here. You could do that 1,000 times, and then you would find, of course, a bearing capacity that would not be a single number, but that would also have a probability distribution. And in this case, with a footing on an undrained clay, you would have a distribution of the limit load, which would be affine to the distribution of the undrained shear strength, because the limit load is, of course, directly proportional to the undrained shear strength. So that type of analysis is not necessarily really that interesting. When it gets interesting is when you start accounting for spatial variability, and that's done with this so-called random field concept, where the idea is we still have a mean value and a standard deviation, but in addition to that we also have so-called correlation lengths. And what are correlation lengths? Well, correlation lengths are the lengths at which the parameters are significantly correlated, roughly speaking. So what I mean by that is you go out into the field and you do a CPT, for example, and you find an undrained shear strength of, say, 50 kPa. then if you go at a distance, if you do another CPT at a distance of 1 meter from the first test, well, then you would probably find something that was kind of similar. If you increase the distance to 10 meters, then you might find something that was not necessarily that similar. If you go to 100 meters, then there would be even more difference. If you go to 10,000 meters, well, then it might be very different. So there's some correlation depending on the distance between sampling points, and that is what is quantified by the correlation length. So a large correlation length means that the parameters are correlated over a large distance. A small correlation length means that much more rapid fluctuations spatially. And what we've done in OptumCE is actually operate with two correlation lengths. We call them CLX and CLY. So a correlation length in the x direction horizontally and a correlation length in the vertical direction, in the y direction. And a typical field of a parameter is again an undrained shear strength generated with this random field concept is shown here. This top one here has a horizontal correlation length of 50 meters and a vertical correlation length of 1 meter. So things are fairly well correlated as you go horizontally and much less correlated when you go vertically. So much more, many more fluctuations when you go vertically. And you have to be careful with making these assessments, of course, but if anything, this would not necessarily be unrealistic, just because of the way soils are deposited. The history, the stress history would tend to sort of favor this type of layering. You could also, of course, have equal correlation lengths, then you might end up with something like that. So this is 1 meter and 1 meter. You could switch this one around, so have a small correlation length horizontally and a large one vertically, and then that's simply the one up here, turned 90 degrees, and you can have large correlation lengths in both directions, meaning that there's really not a lot of fluctuation within the correlation length. So I would say, and that's what's been kind of, I wouldn't say verified very rigorously experimentally or through site investigation, but these numbers are, if you're to believe the literature, these numbers are fairly typical. So a much larger correlation length horizontally than vertically, leading to this kind of layering. And then when you, so this is from the manual, I would advise you to go through that. And then, of course, there's an example here. It's simply bearing capacity of sort of a most classical geotechnical problem, probably a strip footing on an undrained clay. And this is for a fixed, say a deterministic analysis, or for a fixed SU, we have the famous 2 plus pi times SU as the bearing capacity. And then as we add variability, well, then we get a probability distribution for the factor of safety it is in this case that we plot. And note also that the correlation lengths, of course, should be compared to the let's say the characteristic dimensions of the failure mechanism, which again is governed by the characteristic dimension of the structure, in this case the foundation. So when I say a correlation length of 50 meters, well, that should be compared to the width of the foundation in this case. And then what I've done here is I vary the width of the foundation and keep the correlation length constant, and as the width of the footing approaches the correlation length, as it gets wider and wider, then we get something that is tends to sort of be just in the ultimate case a Dirac delta function. So the variability can't really be seen anymore. But and similarly, if the correlation length is very, or if the footing width is very small, well, then it just basically corresponds to having the correlation length is infinite, meaning that the footing can only really see one undrained shear strength, namely the one right out underneath the footing. So it's all explained here in the manual, I think, a little bit better than I'm able to do now. So have a look at that. And interestingly enough as well, I think this is really one of the more interesting things that this thing can be used for. It sort of gives some insights into how much soil is actually mobilized in typical failures. So one thing, of course, is the bearing capacity. Another thing is, or in this case, the factor of safety. Another thing is that might be of interest is how much mass is actually mobilized, and you can see that depends entirely on how exactly the layering is the layering that results from this random field generation. Sometimes you have a weak layer on a strong soil, so then you have a very shallow mechanism. Sometimes you have a deep weak layer on a stronger soil, well, then you get something like this. And if you have a strong layer that you have to punch through first in order to get down to the weaker layer, then it looks something like this. So this is, I think, it's kind of interesting. It is particularly interesting when it comes to slope stability because, well, not all slope failures are really created equal. There's often the analogy with a skyscraper. If you have a 100-story skyscraper and a window on the 57th floor breaks, well, then in principle the structure has failed. But of course the consequences of that failure are very small. And in the same sense, you could say for slope stability, well, some failures are more serious than others. Failures involving a large mobilized mass must necessarily have higher consequence than ones involving not so much mass. And so again, depending on the layering implied by the random field generation, you have more or less mobilized mass in your slope failures. So you can have a depth-dependent strength as well. So have say a linear variation of the undrained shear strength with depth, and then add variability on top of that, let's say linear or linear trend. So you can generate random fields like this one here, where you have a trend to a linear variation, but you have some noise, you have some variability. And it is not only for strength this concept applies, it applies to any material parameter that is available in OptumCE2. So you could apply, you could work with a random stiffness as well in elastoplastic analysis, and you can work with combinations of stiffness and strength parameters. So so again, I'd encourage you to have a look at the manual, just very briefly to show you how to set up a problem, to how to run a stochastic analysis. So I'm going to run, say, an embedded footing problem like that. Let's make that rigid. Let's give it a unit weight of, say, 23, and then have a Tresca material. Let's make it 100 kPa undrained shear strength, and then standard fixed T's and a load on top here. And I'm going to run limit analysis in this case, and I could say, let me just keep it at 1,000 elements, at 100 elements, just to get things running quickly. And then, yeah, I mean, the undrained shear strength, I set it to 100, but of course that is the one we want to have some randomness in this case. So I open up, click the P here, and I open up this material parameter dialog. I go to random. So 100 here, that's going to be the mean value. And then I have a choice between a normal distribution or a log normal distribution. I'm going to pick the log normal distribution in this case. Now, COV, what's that? That's the coefficient of variation. That's basically the mean value, or sorry, the standard deviation divided by the mean value. So it's a dimensionless measure of the variability, you could say. And I could set that to say 20%. And I could set the horizontal correlation length, let me just set it to 50, and I could set this one to 1 meter. And that's it, and you'll see there's random appear here in this SU field. And then I'm now pretty much ready to run. I just want to switch to project, and then the number of Monte Carlo runs. That's the number of runs that I'm actually going to do. So I generate one random field, do one run, generate another random field and do another run, and so on. And I do that, by default the number here is 1,000, but I could set it to say 10. Then there is a seed. That's explained in more detail in the manual, but it's not so important. We can leave that at 1. The expansion, that's the KL. We don't really have any other choice, so leave it at that. And terms and expansion, usually 1,000 for these types of correlation lengths that we're dealing with here is sufficient. So we can now run, and when you do that, well, so random fields are generated and then limit analysis are run. And if we then go to PDF, that's the probability distribution function, you can see that it looks like this. There's the load multiplier and the PDF, the frequency, and there's also the cumulative distribution function, which looks like this for these 10 runs. That was not very much, but so let's just try to increase it a little bit and then see how these graphs change as the results come in. The CDF is in many ways more interesting to look at than the PDF. And since this is the integral of the PDF, it also tends to be less noisy, so it tends to converge, if you like, faster. So the question is, how many runs should you do, and that's discussed in the examples manual as well. I typically recommend. Yeah, well, I mean, that's a good question. Depends what probability of failure you're looking at. I mean, are you looking at the very tail end of the distribution? Then you really need a lot of runs. If you are not at the tail end, then you need less. So it's to some extent problem dependent, but it's very much problem dependent. In the examples described in the examples manual, 1,000 runs turns out to be quite all right. And you can already now start to see this S shape that we somehow in one way or another expect for the CDF. And where are we? Well, we are at run number 70 now. PDF, well, yeah, you can start to see something that kind of looks like a log normal distribution as well, which, or something similar to a log normal distribution. It's not going to be exactly a log normal distribution, but this is sort of how it looks. And let's just wait till the results are in. You can see here load multiplier varying between, say, there's a very low probability of about 450 up to about, say, 800. So quite a range of variability in the load multiplier. And I think we are done now, yeah. So that's the final state. And the results shown here are for the, it's not going to look very nice because it's just for 100 elements, but the results are referred to the results of the last run. So just be aware of that. SU, yeah, well, I mean, since it's such a coarse mesh, it's not really going to look very good. So if you want to recover the results of a particular realization of a particular Monte Carlo run, you can do that using this by setting this seed, but that's all described in the manual. I won't really go into details about it here, but you can recover the results of all runs if you really want to. Now you can also go to XY plots, and then the results are available to be plotted here. The load multiplier, the cumulative distribution function, the CDF, that's the one we saw before, and as usual you can click this and the data is available over here if you want to copy, paste it into some other program, and the PDF as well. I think that can be actually copied as well, yes. The data for that is available as well. And what else is available? The mobilized mass. Yeah, I should first say the load multiplier. That's the load multiplier for the different runs, right? So it's up and down. And there's the mobilized mass. That's up and down as well. And if we look at the cumulative distribution function for the mobilized mass, well, it's sort of an S shape as well. And the PDF looks like that. So it looks not exactly like the PDF for the load multiplier. So there's not necessarily a direct relation between the amount of mass that is mobilized and the load multiplier. But that is how it is. See you next time.